acids and bases. And the only ones that we're going to be like looking at for this, it's how to write something acting like an acid when it's in water, and how to write something acting like a base when it's in water. So we're not going to put an acid with a base. We're just going to put them with water for right now. And so we're just going to show what happens when it's in water. So we start with acids. So up here, I have the two basic things that you have to understand. And both of these are important when it comes to how to write down what happens in water. The first thing, what the acid does. The acid will donate a hydrogen +1 ion. Now, when I say donate, I don't mean that it just goes and floats away. A pair of electrons that's on another atom comes in and steals a hydrogen from an acid. So it doesn't just float off, it gets pulled into a covalent bond on another atom. When we're talking about water, it's going to be a pair of electrons on water, on the oxygen, that then take a hydrogen off of the acid and it bonds it to water. When that happens, it forms H3O positive in water. So both of these, this is what happens to the acid. It has a hydrogen and water comes in, the oxygen on water comes in and takes it. So just to kind of show you in terms of a structure, what happens. If we just do the Lewis structure for water, there it is. In order for this to happen, the thing that, which is water, that is going and taking a hydrogen from the acid, which is going to be donating the hydrogen, it has to be a lone pair. The oxygen has 2 lone pairs. And so, let me do a different color. Can't see that. There we go. Okay, there's HCl. Okay, so this is partially positive and oxygen is partially negative. And so they are molecules. And so the polarity of this causes this pair of electrons to be attracted to this hydrogen in a dipole-dipole bond interaction. But what ends up actually happening is this pair of electrons goes and grabs hold of hydrogen and tries to take over the orbital that's being used for a bond. And when that happens, hydrogen has to stop bonding to chlorine. And so that arrow is just showing the electrons going and getting that hydrogen. That arrow is showing that bond is breaking. And what ends up happening is you end up with water. It still has that lone pair, but this other lone pair now has decided to bond hydrogen. So now water is no longer water, it is H123O. It has a positive formal charge because oxygen has 3 bonds and 2 dots, and 3 + 2 is 5, and 6 - 5 is +1. So the formal charge on oxygen becomes +1. Okay, the HCl, when it lost its hydrogen, what ends up being left behind is chloride. So chloride is a negative. And so HCl is the acid. it donates its hydrogen, which means it loses it. When it loses it, the chloride's left behind, and the H goes to water because we're showing the interaction and dissociation in water. Okay. So in order to show that in terms of a reaction, you actually have to write water as one of the reactants because you have to have it sitting there. You have to have one molecule sitting there that can receive the hydrogen. There's plenty more that are not receiving a hydrogen. That's the aqueous part of it. This is just the one that's sitting there receiving the hydrogen. And so the generic format would be, this is your acid where there's the H, and you just take, it'll just be one H that you remove. This substance will lose one of its H's, and when it loses it, the rest of this, whatever it was, is left behind, but it lost a positive, so it becomes negative. And then the positive hydrogen goes to water, so there's your hydronium. So automatically it'll be, you'll see water and hydronium. And then whatever the acid is goes there, and then you write the same formula with one less H, and its charge changes by -1. Okay, so here's an example. HF, hydrofluoric acid, aqueous. So there's your HF, so generic HA. It's aqueous, so it's being surrounded by water. And this is the water that's sitting there ready to receive an H. And so if we give this water an H, it becomes H3O. And if we take a H off of HF, it becomes fluoride. And those are both aqueous. They are dissolved in water. Okay. So there are two things that I want to point out up here. When you write the dissociation, if it's weak, you will get equilibrium arrows. But if the acid is strong, it will be a one-way arrow. So all acids do this in water, but what does one way mean? It means that it would mean that every bit of the acid gave away the hydrogen to the water. So it's one way. Equilibrium, this is equilibrium. This is a weak acid. This means that everything you see is present. So if you had a solution of hydrofluoric acid, you would see at the atomic level, you would see HF molecules and you would see fluoride. So all of the HF didn't like lose its hydrogen and just turn to fluoride. Whereas this HCl is strong. And so this would actually be a one-way arrow. So when we dissolve HCl in water, every single HCl molecule turns into hydronium and chloride. It's an acid, not because of chloride, it's an acid because of the hydronium. When you dissolve NaCl in water, it doesn't turn into HCl. Okay. If it is HCl, then that creates hydronium, and hydronium is what makes them to be acidic. Okay. Next week, we'll calculate pH, which is a measure of the hydronium in water. So not the amount of HCl or HF, but the amount of hydronium. Okay, so if it is strong, it's one way. If it is weak, it is double because it's equilibrium. There are only 8 strong acids. I put one of them down here and I put strong. Everything else would be weak, but I'll go ahead and list the strong acids. And again, strong acids are not equilibrium. Equilibrium is when only part of them dissociate. If it's strong, all of it does and turns into hydronium, which would then cause the pH to drop. Okay, so strong acids, HCl, HBr, HI. So the halogens, except for fluorine, HF is not strong. HF is weak. Okay. HNO3. These are ones that are created by dissolving gases in water. So nitric acid, sulfuric acid, chloric acid, perchloric acid. They have a lot of oxygen. So these are just a few of the elements when they are completely like loaded up on oxygen. It turns them into very, very, very weak bonds to hydrogen. And a weak bond between oxygen and hydrogen creates a strong acid. Because if it's weak, it breaks easily. And so just dissolving it in water would break it. And then the last one is one that I didn't even know existed until a few years ago, because I've never ever seen it, except in a data table. And that is thiocyanic acid. I'd always said 7 strong acids. And then I look at a table and there's like right next to that one, it said strong. And I was like, oh, okay. So Mr. Walker still says 7 strong acids because I taught him 7 strong acids. There's probably more now, but there's a, and that one, that one's not common. This one is this one right here. This one and nitrate, nitric acid, and this one, we usually don't use them for acids because they oxidize things so crazily that we usually use them to oxidize, like for the oxygen content, not for the hydrogen. And so we used nitric acid to react with copper because the other acids don't react with copper. So it wasn't the acid that reacted with copper, it was the nitrate. Perchloric acid, it is more of an oxidizing agent than even nitric acid. So if you look at our hoods in lab, they say that's not safe for perchloric acid. Not because of the acid, but because it's such a strong oxidizing agent that if the gases go up into the hood area and then recrystallize because they're big and they create ions, then those crystals are an explosive. And so if something goes up and then reacts with the crystals, then you can have a fire inside of the hood. We don't have any of these. We have sulfuric and nitric, but nitric gets stuck in its own spot. It can't be stuck in the acid cabinet. It has to be in its own spot because it oxidizes things. So it's dangerous. So anyway, strong. Everything else is weak. Again, strong means that you would do a one-way arrow. One-way arrows mean that when you have HCl or HBr, HI or HNO3 or any of these in water, that formula has lost a hydrogen completely. And so you would not, for the nitric acid, you would not find any H bonded to nitrate. It would all be nitrate plus hydronium. And all you got to do to change is you would just do a one-way arrow. Okay, so let's do this first one. So each of these is do the acid dissociation. And so you put the formula, and I give you the formula, so just write it down as you see it. So this would be the acid, H2PO4 -1 aqueous. And then you're going to put plus water. These are not ionic dissociations. Ionic compounds dissociating. This is acid. And so you have to put plus water because you have to show the formation of hydronium. Different format because it's a different kind of interaction. So what is going to happen to this formula here, this H2PO4? It's going to lose one H. I know there's 2 there, but Once it loses one, it is no longer H2PO4. So whatever the formula is, you just pull one H off of it. And so what would the formula be if you pulled one H off? HPO4, and its charge it becomes more negative. It changes by -1. So it increases its negative by 1. So it goes from -1 to -2. Because now there's 2 oxygens that are missing a bond. But so when you pull a positive off of your acid, its negativity increases by -1. Okay. Where did the hydrogen go? The water turned into H3O positive. Oh yeah, I got to put AQ. 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 So the acid donates the hydrogen, and so its formula has one less hydrogen than it had before, and its charge increases by -1, one more -1, and the water turns into hydronium. General format. Okay. So for these, you want to just focus on pulling one hydrogen off and rewriting the formula, making sure its charge goes up by -1, and then make sure you have the hydronium and it's positive. And those are, everything's aqueous except water, which is liquid. Okay. Okay, for bases, these are only going to be the weak bases.